All right, so in stats topic 6, we're going to be talking about probability models. And before we go into probability models, we need to talk about what a fair game is. Now, we have to think about fairness in a more formal matter. So a lot of times we use fair as informally. So it's not fair that Johnny has more video games than me, and it's not fair that Susie didn't have to take Spanish this year. So technically that is a very informal definition of fair. Those are a matter of opinion. So when we talk about fairness in terms of probability, we're talking about it very formally in context of games or making choices. So first off, a fair game you can define as where every player has an equal probability of winning. Okay, so everyone's equally likely to win. Or instead of talking about players, you can talk about options. So it's all possible options have an equal probability of being chosen. So let's look at some examples. So a class of 25 students wants to choose 3 students at random to bring food for a class party. Any set of 3 students should have an equal chance of being chosen. Which of the following strategies will result in a fair decision? So the first one, the students line up alphabetically, and each one in succession flips a fair coin. The first 3 students to flip a coin brings the food. So if we think about this, for it to be considered fair, everybody has to have an equal chance of being chosen. And if I'm putting them in alphabetical order, and it's the first 3 to flip ahead, this is not going to be fair, because not only do all students not have a chance of being chosen, all students don't necessarily have a chance of even flipping the coin. Okay, so what happens if the first 3 people flip? People with last name Z don't even get a chance to flip. So this would be not fair. And I'd probably write it off to the side so you have room. And then you always want to kind of explain why it's not fair. So all students are not guaranteed the same chance to flip. So then we look at B. Each student draws a card from a well-shuffled deck of 52 cards. The teacher shuffles a second deck of cards, spreads them out, and draws cards one by one until he matches cards of each 3 students. Now here, everybody's getting a card, and then he's randomly going to pull 3 cards and to see which ones match. So here, this would be considered fair. Because all students have the same chance of being selected. All right, so go ahead and pause the video and try the U-try. So this one is not fair. So the siblings do not have the same chance of success, okay? One sibling will be faster than the other. They're not going to exactly tie. It doesn't matter which sibling, it might change and fluctuate day by day, but to be fair, by definition, everybody has to have an equal chance. It is not our quote-unquote, like, understanding of what fair is. Just because they agree to it doesn't mean that it's fair. So, for an event to be random, there has to be no predetermined pattern or bias towards any particular outcome. So it's very hard to get fair decisions, Okay. One way to help us make fair decisions is to use numbers. So one way we can use numbers is using what we call a random number table. So it contains a random digit of numbers 0 to 9, and we can use these to model randomness for sampling purposes. So I've got part of a random number table. So typically there's spaces inserted every 5 or every 3, just kind of help us break it up and read it. So a coach wants us to select 3 players for her basketball team at random to lead warm-ups before practice each week. The coach assigns each player the numbers 0, 1, 2, 1, 5. How can the coach use a random number table to choose the 3 players? So one thing that's important is that we're going up to 15, so all of our numbers here are double digits. Okay. If I was going up to 100, I would use 3 digits. So 1 would technically be 0, 0, 1. So what I'm going to do is I'm going to look at my random number table in pairs. So I'm going to look at pairs of numbers in the table. Until I can choose 3 numbers between 0, 1 and 1, 5. And I'm going to ignore repeats and numbers that are too high. So for example, if 18 comes up or 72 comes up, I'm going to ignore those, and I'm going to keep going until I have 3. So I'll start with the first line, and I'll go back here. So my first number is 87, so I don't choose 87. My next one is 49. I don't choose 49. 43. I don't choose 43. 97. 07. I'm choosing person 7. So whoever was the number 07. 20. 52. 59. 57. 04. 04 is one of the numbers that I'm looking for. It's between 1 and 15. Then we go 48, 36, 12. 12 is the last number that I'm looking for. So now I have 3. Now if I'd used a different row, I would have gotten different answers. And that's okay, because it's supposed to be random. Everybody has an equal chance of being chosen. So I want you to try the you try here. So go ahead and pause the video. Now read the prompt. It's asking that they alternate assigning teams. So you'll have team 1 and team 2. So the first person will go on team 1, the second one will go on team 2. And he's going to use the second line of digits from the number table. So go ahead and pause this, try it, see if you can get it. All right, so check your answer. Team 1, you should have gotten 16893, and team 2 would have been 45270. Here's kind of the first number is 1, so that goes on team 1. The next number is 4, so that goes on team 2. We can't choose 1 again, so the next person is 6, that goes on 1. Can't choose 4, can't choose 1. 5 goes on team 2, and so forth until everybody gets chosen. And then, is this fair? Yes, because everyone has an equal chance of being chosen, since number tables are random. So we can also use probability models to assign probabilities to the outcome of chance processes to make decisions about real life. So problem 3, a restaurant gives away 4 different toys in their kids' meal. Each meal contains exactly 1 toy, and the toys are equally and randomly distributed. About how many kids' meals would a parent have to buy to get all 4 toys? So here, you would not expect, if all of the toys were random, to go to McDonald's and have to buy 4 Happy Meals and get the 4 toys. It just doesn't work like that. So generally, you're likely to get doubles, sometimes triples, depending. So about how many would we have to do? So one thing that we can do is that we can use, we want something that has 4 different options. So we can use a random number table, or to mix it up, we can use a spinner. So what we can do is we can spin this spinner and see how many times would I have to spin it so that I get to land on each option at least once. And I'll link a spinner in the problem as well. So I'm going to go ahead and do this, and I'm going to record my spins. So here are my results. It took me 9 spins to get each one, so I would have to buy approximately 9 Happy Meals to get all 4 toys, or 9 kids' meals. Now, just doing this once is generally not a good way to do this. What you want to do is do this multiple times. So I'm going to pause the video and run this simulation multiple times and just count the number of spins it takes for me to get all 4 toys. So I'm going to do it maybe 25 times. Okay, so here's the data of me doing it 25 times and how many times it took me to get all 4 spins. So what we're going to do is we're going to find the average of this. We're going to add them all up and divide by however many we're adding. Now let's not forget to add my original 9 from here. So when I add them all up, I get 220. Hopefully I added correctly. And I have 25 different times that I did this. So we'll divide that by 25 to get approximately 8.8. And so we need to order about 9 Happy Meals, or 9 kids' meals to get all 4 toys. Let's go ahead and pause the video and try the U-try. Pause the video and try the U-try. All right, so one way we could describe this is that we can roll a number cube until we get a 6. We want to make sure we keep track of the results and how many rolls it took. We repeat, this is the key, we need to make sure we repeat this several times and take the average number of rolls needed. All right, number 4, a pharmaceutical company is testing out the effectiveness of a new drug for asthma patients. Out of 160 volunteers who suffer from asthma, 60 are given the drug and 60 are given a placebo, which has no active ingredients. So after 2 weeks, volunteers are asked if they noticed improvement in their asthma symptoms. The results of the survey are shown in the contingency table below. So A, B, C. So A, what's the probability that a volunteer noticed improvement in symptoms given that they received the drug? So it's given that they received the drug. So this is out of the number of people who received the drug. So out of this group of people. So the probability that they improved, well, there were 67 out of those 80 that approved. So this is 0.8375. B, what is the probability that a volunteer received the placebo given that they did not report noticeable improvements? So the given was that they did not have improvements. So we're only looking at the people that did not improve. So we're only looking at this group of people. So what is the probability that this group did not improve? Well, there was 56 out of the 69 that did not improve. So this is approximately 0.8116. So the pharmaceutical company decides to produce and distribute this drug. The drug is marketed as an effective way to improve the symptoms of asthma. Based on the results of the test, did the company make a good decision? All right, so the probabilities we calculated above showed that 8 out of the 10 that were given the drug improved. Also, about 8 of the 10 that did not improve were on the placebo. The company made a good decision. What this does is it does not take into account these people here, and these are the people that are suffering from the placebo effect, where you think something is working because you think there's been like a change, but really it's not working. Right, and that's all I've got for today. So go ahead and get started on the worksheet.